Woohoo, we are live. This is Math 60, Intermediate Algebra, and this is an introduction to functions part 2, and we are moving into graphs and then something super fun called function notation. And when I say super fun, I mean make sure you have your comfort animals nearby, a support system in place, and perhaps a nice fruity drink of some sort to console yourself with, because it can get a little bit confusing, but I'm going to do my best to try to lay it out very clearly so it'll make perfect sense, and then win-win, right? Woohoo! So we're going to start off though with graphs and looking at graphs to understand more about a function or a relation is basically going to happen for the rest of math. So as long as you're in math, almost every single class you take will involve graphing. So this is how we visualize functions and relations. And so I'm going to start with this, and I'm going to say that it was not possible for me to put this into the image to begin with, but you should assume that this function ends. Now, I don't take it for granted. I am very careful. Either I put a very clear dot, which means it ends at a point, or an arrow, which means it keeps going. Some graphing apps and such are a little more lazy about it, kind of cool about it, but they don't give all the information. So if you're ever curious, if you're ever confused, ask. Let me know. I can help you figure it out. Okay, so does this graph describe a function? In order to look at this, I'm going to need either a ruler, which I have suddenly misplaced. Don't you love that? Where's my little ruler? Oh, arg, my ruler has gone on walkabout. Oh, well. Okay, well, or a helpful puppet stick, also known as a chopstick or a hashi. You need something to visualize a vertical line. That's what we're going to be talking about. So how are we going to use this lovely manipulative? Well, what we're going to do is I'm going to first look at the domain and range. And again, this graphing app that I stole this image from does not give you X and Y. So let me be a little more explicit. X is there, Y is there. If in this class we don't write that in, you should assume X is the horizontal and Y is the vertical. That's kind of the standard. As you move into other classes, however, you will find that sometimes we switch that around or change the variables altogether. So most of the time, X and Y, and I've got my arrows, and okay, everything is nice and happy. So let's look at what the domain is. Now, it's a little bit hard to see, especially, I think, in the video. So what I'm going to do is I'm going to write in, if you could get really close to this, you could see this. I'm going to write in that this point is the number -3 in the X coordinate, and I'm going to say -10, yes, in the Y coordinate. And up here, this one's a little bit harder. And if you get in close, you could see. And I believe this is 1, this is 2. So this is intended to be 2.5 or 2.5, your choice. And then that's the Y coordinate is 40. So let us go ahead and we'll just agree that these are the coordinates. What is the domain? So remember, the domain is the one that domain comes before range in the alphabet. X comes before Y. So what we're looking at here is all the X's, and notice this is continuous. It doesn't stop. There are no breaks. There are no gaps. Nothing is missing in the middle. It keeps going all the way from X equals -3 all the way to X equals 2.5. So I could do this with brackets because these are closed points. They're not open points. Or I could say -3 is less than or equal to X is less than or equal to 2.5. So this is the inequality. And this is as an interval. So that's what these are called. This is giving the answer as an interval. This is giving the answer as an inequality. Let's look at the range. Those are the y's. That's top and bottom. So what's the smallest y value? Well, it looks like it starts off, even though it goes swoop-de-doop around, and it does go up and down, I think the lowest point is right there at y equals -10. And it goes up and then down. And I think the highest point here is at 40. So -10 to 40. And be careful here because it's the range. So we're going to set it up the same way, but you write it with y instead of with x. Does that make sense? So x ranges, sorry, that's an English word that's awkward. X is going to span from -3 to 2.5, and y is going to span from -10 to 40. Okay, so we got a domain and range. We know that's the box that this function lives in, but is it really a function? Am I being premature? And so what is a function? A function means each x corresponds with 1 y, not 2. So what would 2 y's look like? Well, if I picked a value, let's say x equals 0. So here, what would 2 y values look like? Well, it would look like that you would have a point maybe here and a point there. So you'd see 2 points stacked up. This would be a really weird graph. Normally, when you're graphing, you expect if there's an x, like this point, x equals -3, there's 1 y value, just -10. When x equals 2.5, y equals 40, right? So you're expecting 1 in, 1 out. And so the possibility that you could have an x, like x equals -2, I know this is very small in the video, but that's -2. There's a point right there, just a single value for y. And for this, when x is -1, y is 0, just a single point. And right here, when x is whatever it is here, right, that value of x corresponds with just one value of y. Yes, this is a function. So I mentioned the stick. What the heck is going on with the stick? Well, if you have a stick or a ruler, this can be anything you want. I mean, it could be a pterodactyl, it could be a brooch, it could be a vertical. Oh, that's not very vertical. There we go. A vertical line. Ooh, look at that. So what you do, and you don't have to have a stick, or you could use your hand, or you could just use your imagination. But basically, you go along the graph and make sure the graph only ever intersects this vertical line one time. And that's true. In this graph, it only does once. So I know you're asking, but what does it mean? What does that mean? Show us the other example. Okay. Almost as if I'm psychic. Ooh. I've got an example of a problem where this is a mess. Notice that if I draw the vertical line, if I imagine a vertical line right here, which I'm going to draw in with a little blue line. Oh, you know what? The graph itself is blue, so let me do purple. Yeah, let's do purple. So let me draw in a little purple vertical line. How many times does that vertical line run into the graph, intersect the graph? And the answer is it intersects 2 times. So it turns out circles are actually, even though they're such a pretty shape and they're nice and basic and, you know, just all around a really helpful tool, they are really kind of rough to deal with in math. Now, we will get to them. They're one of the last things we do in this class. There's graphing of circles, and if you get really excited and continue on through math, there's trigonometry, does a whack ton with circles. There's another algebra class that works on circles. You even have to deal with circles and calculus. You know, circles are very exciting, but we're going to kind of slowly sneak up on them because they pose a problem. And the problem is vertical line intersects twice, which means this is not a function. So, and if a vertical line ever goes through the graph twice, ooh, that's exciting. Okay, so if you're seeing this, I'm going to practice some editing. I just got a phone call. That was very exciting. And I'm filming this with my phone. So if you're watching this, then this means I have learned to edit my videos. Dun, dun, dun. And if you're not seeing this, then I'm not actually sure what that means. If you're not listening to me, then do I really exist? Maybe I'm in the void. Okay. Anyway, we were talking about vertical lines, speaking of the void. So if the graph intersects the vertical line more than once, it's not a function. It actually is going to be something that's very difficult to deal with, because I could say, when X is right here, what's Y? And you would have to say, well, sometimes it's up here and sometimes it's down here. It's very Schrodinger, you know? Is the point in the second quadrant or is in the third quadrant? And the answer is both points. And spoilers, what we're going to do for the most part to deal with it is we're going to chop it in half and deal with just the top half or the bottom half, because dealing with both at the same time is just really hard. So that's what we're going to do, but not today. Today we're just going to say, whoa, this is not a function. We can still look at the domain, and I don't know if you can see on the in the video, but the domain of this, it goes from x equals -1 all the way to x equals 1. And the range, it's a circle, right? So there's a symmetry to it. The range goes from y equals -1 to y equals 1, which is kind of nice. Remember to put in the y for this one. Does this graph describe a function? No. But we can still look at domain and range and say, wow, isn't that interesting? I sure hope we'll be able to deal with this better in the future. Okay, I'm going to peek ahead. Okay. So now we're going to go into a topic that is vital, but it is a brand new language. This is not the language we've taught you up till now, unless you've taken more math. If you've taken more math, then you might be familiar with this, but some of you may be brand new. Again, be gentle with yourself, because this is brand new and it's going to seem a little weird and it's going to seem really annoying at first. I hated this. I was like, this is stupid. Why are we even doing this? And now I know why we do it. And all I can do is say it does make things easier in the long run. It's just going to take a little bit of patience now. This is called totally, I know, it's like, whoa, you just changed subjects completely. I know. We do that in math. We get excited and then we go all over the place. So we're going to embark on something called function notation. What the heck is that? Well, this is going to be a quote unquote easier, which it won't be at first. At first, it'll be just like, oh, I hate this. But in the long run, it will be hopefully easier to do. So let's see. Up until now, we've got y equals 2x is how we write things. Like if we had an equation, y equals 2x. The new way we will write, so this is the old, and this is the new. Instead of y, we're going to name the function f for function. It's kind of nice, huh? F, and then this is pronounced f of x. Let me write that down so you don't forget. F of x. Now, I know it looks like f times x. And trust me when I say that if I had been around back when everyone was developing these notations, I would have been like, this will confuse students a lot. And all of the old mathematicians would probably just laugh, because, you know, they would. And then I would be burned at the stake for knowing math. It would be awkward. But I would have tried. But I recognize that parentheses at this point are now being used for like 3 or 4 completely different things, right? Parentheses are multiplication. right? Order of operations with multiplication. They're being used for ordered pairs. They're being used for intervals, which look just like ordered pairs, and that's all a big mess in itself. And now they're being used for functions. That is so over the top. I know parentheses really are kind of extra, right? So we're going to do our best. I'm going to convince you that with practice, you will get used to this. So this is a lot like having synonyms in a language. You know, like I can't think of a single one off the top of my head, but like the number 2, which sounds like I want to go to. 2 is a direction. I want to go to the park. When I say I want to go to the park, eventually you learn, oh, you don't mean 2 parks, you mean going from here to there. So different words that sound the same. Parentheses have different meanings, even though they look the same. So let's take a look. Now, it turns out that I can talk all about this, but until you see it in action, you're not going to get it. So I'm going to ask for suspension of disbelief. If you believe that you could watch a movie about a guy who turns into a giant green monster, and like that his eyes get bigger and smaller, and that his muscles get bigger and smaller, and then his heart gets bigger and smaller, then you can watch this video and trust that if you just let it wash over you, you might have to watch it more than once, but this will start to make sense. So deep breath, everybody ready? We can do this. I trust you guys are awesome. You can do this. Okay, so here's my function. F of x equals 2x, right? The one I was talking about up here. So the first thing you should ask, is f of x always 2x? Do I have to memorize this? And the answer is no. This is f of x is a name, like say Amelia. If you met one person named Amelia, and then you met another person named Amelia, would you think they were the same person? And the answer is no. So this is a function that happens to be named f in this situation. F could be named anything. I mean, really. So if f of x equals 2 times x, that's the rule. What is f of 3? So what I want to point out to you is for this, if you've got f of x equals 2x, you could also think of it as f of box equals 2 times the box. Whatever's in there gets multiplied times 2. Okay? So that's the rule. F of x is 2 times x. F of box is 2 times box. F of 3 is 2 times 3, which is 6. F of 0 is 2 times 0, which is 0. So here, again, whatever is inside the parentheses there, you multiply by 2 for this particular function. Okay, it's the rule. Okay, now we've got one named g. If g of x equals x, again, let me point out, if g of x equals itself, that means whatever you put into the parentheses comes out as the same thing. Whatever goes in comes out as itself. You don't change anything. This is kind of a silly, what we sometimes call a trivial function. But this turns out to be a very important function. It says whatever number goes in comes out, and sometimes that's very helpful. So g of 1 equals 1. G of 2 equals 2. G of 0 equals 0. G of pi equals pi. Whatever goes in comes out. And I want to add one more because I wasn't thinking of doing this one, but now I want to do it. G of t, and I know everyone's like, whoa, what are you doing? And the answer is, once we have function notation, we can just go bonkers. We can have any variable we want. We can have any values we want. We can just explore the universe. We could have a big old function party. G of t equals t. Now, should you memorize this function? No. This is what g of x is right here, right now. As soon as we walk away from this paper, as soon as I pick this paper up, this paper will not, this function will be different. G's are going to be all over the place. Okay, so far so good. Remember, you can always set up time with tutors, set up time with me, come to my office hours, ask, and we'll drill. We'll just go over these. And I know it sounds unbelievable, but it's very much like practicing anything, like working out, like practicing a language or practicing with an instrument. Over time, it will get easier, and then a light bulb will come on. You'll go boom, and then you'll be like, oh, that's right. I mean, your head won't explode. Actually, that would be messy. We wouldn't be able to teach math anymore if that's the case. Oh, that would be so awkward. Like all your math teachers would be wanted, you know, and it would be, maybe it could be a cool video, a cool TV show about how we're rebels and we're teaching math. Okay, I know that I went too far there. Okay, it turns out that the simplest functions, and again, simple doesn't mean easy, simple means fewest moving parts, is actually a constant function. But it takes a really long time to get used to what the heck this is. So what does this say? This says h of x is 12. So in other words, oops, I got excited, drew the box first. Whatever you put in, doesn't matter, it's 12. This is like going to the DMV. If you've ever been to the DMV, no matter what's happening, you need to register your car. You need to get a new driver's license. You need to pay a fine. Whatever it is you need to do, they always send you to line 12. Now, there are people who are available to help you in all the other lines, but the person at the front's like, no, you go to 12 and you wait. So this is like the DMV. So you come in with a 1. What do you go to? You go to 12. You come in with the 0, 12. Come in with the 12. Ooh, tricksy. Your brain's going to notice, wait a minute, these are related. It's a coincidence. H of 12 is 12. H of anything is 12. It's a constant function. In the long run, this is easier because you just write the same thing every time. But in the beginning, when you're first learning about it, this can be very strange. Like, why would you do that? And the great thing about math is you don't need a reason. We're just studying patterns. So we're just practicing patterns. So you're looking at what I do and you're like, okay, I can follow this pattern. Okay. You guys ready? You might want to go get a hug if you have puppies or pictures of puppies or, you know, videos of puppies. Maybe go take a break. This part takes some patience, but you will get it. I promise. You will absolutely get it. Okay. These are more complicated functions. I have brand new f and g. F of x is now x squared, and g of x is x plus 1. So again, when we write these out with the boxes, f of box is whatever is in the box squared. Okay. And g of box says g of x is x plus 1. It's whatever's inside, you add 1. The x in these is just a placeholder. It's just the sample problem, the example, the generic. It's just the recipe. Okay, so what is the benefit of function notation? Well, function notation will allow us to work with 2 functions now. And if I say f of 0, you're like, oh, you want me to do this rule because it's got the name f. But if I have g of 1 or g of 0, you know, I want you to look at this one. So this is one of the benefits of function notation. Okay, f of x is x squared. So the f function is a squaring function. F of blank is blank squared. So f of 0 is 0 squared. F of 2 is 2 squared. Are there any other f's? There's another f right here. F of 1 is 1 squared. Okay, don't look at this one yet. Let's go to the g's. G of 0. Now, what does the g function say? G of a box is the box, so whatever's inside here plus 1. So 0 is going to be 0 plus 1. That's 1. G of 1 is going to be 1 plus 1. G of 2 is going to be 2 plus 1. There we go. It's 3. Take a look at that. See what you think. Right? These 3 are following the F rule. And then the G definition of G is right there. Okay. Order of operations holds even when you're doing things that are weird. Order of operations are like our prime directive. And even there, I am actually proving that math teachers are generally, geeks and nerds. What? I didn't say that. What? But yeah, it's the prime directive. If you're not sure what that is, look up Star Trek. Okay. So, hey, Star Trek. F of G of 2. F of G of 2. Order of operation says when you've got a bunch of stuff smashed together, when it's stuffed together, you unwrap it and look at the thing inside first and then at the thing outside. So what's the inside thing? Well, this is F of G of 2. All right. Sometimes it's helpful if you change the way you're writing things. You can also use colors. We've talked about that before. In order of operations, you can, like, the outside parentheses are yellow and the inside parentheses are green so that they're visually different and distinct. Now, G of 2, I know from right here, G of 2 equals 3 right there. So I've got F of 3. G of 2 is right there. So I'm going to put the result of G of 2 in there. See what I did that? So first I'd take G of 2. G of 2 is 2 plus 1 because it's the G rule, which is adding 1, so we get 3. Stick that in there, and then we say, okay, now, so G had its turn because it's on the inside, and then the outside is F. So what's the F rule? The F rule is whatever comes in comes out and gets squared. So 3 came in, 3 squared is coming out. Okay, this is called composition of functions. Composition of functions. When you take a function of another function, there's an outside function and an inside function. Okay, you guys are doing good. This is not easy stuff. Okay, one more, and it's like, well, that wasn't good. Imagine a much better scratching of a record. I don't actually know what that sounds like because I can't imagine ever scratching a record. How horrible is that? But you know what I mean. Sudden change. So now I want to focus a little bit on domains because domains are weird. Domains, I feel like I should have a separate piece of paper. So let me take a moment here because this was never explained to me. I'm going to use the word implicit here because I like that word. Remember, implicit is like implicit multiplication. It means that it's a hidden thing. It's something that is, the domain is, the numbers, I'm trying to think of a way to phrase this, the numbers that won't blow up the function. So domain can be implicit, so not stated, but just understood. And these are the set of numbers that don't blow up the function. A domain can also be given or determined by application. Oh boy, I know you're listening to this, and I if I were listening to this, both Godzilla and Sharktopus are kind of falling asleep here, so I gotta wake them up. Wake up, guys, wake up, or ladies, people, folks, wake up, folks. So let's talk about the differences. So if I have a function and it's 1 over x. What is the one thing? Like, you have one job. What number can you not put in the denominator? That's your one job. X can't be 0 because 1 over 0 is undefined. And that would blow up the function. Okay, so when we talk about the domain, which I just use a big capital D for, because that's what I learned, you can also, if you want to be really fancy, you can give D a name tag. So D sub F means the domain of F. I know you guys are going to be so fancy. Wait till you write to the family or call them on the phone and be like, look what I can do now. I'm so fancy. And your family will be like, oh my gosh, you're the most impressive person on the planet. And you'll be like, I know math. This is great. Okay, so the domain is don't let x be 0. Now, were you told that that was the domain? No, you have to figure it out on your own. And mathematicians tend to assume everyone knows everything, and they don't ever tell you anything, and it can be very frustrating. But basically, they're saying, look, if you're going to use this function, you probably should know already that x can't be 0. Much like, you know, I have bought shredders to shred papers, and most of them, as a teacher, you shred a lot, so I've burned out a few shredders in my time. Almost all of them had no instructions, but I had one that said, please don't let a baby play with the shredder, and don't let the baby get into the shredder. And I thought, wow, that seems unnecessary, right? Don't let x be 0 is just understood. This is, so I'll write the domain is understood. Okay, there's another way to talk about domains. The other way we talk about domains, oh my goodness, this video is so long, I'm so sorry. So glad you guys can pause it and go on. But this is important. This is really important because no one explained this to me when I was studying math, and I was so confused. And I mean, let's be honest, I'm still so confused sometimes. But the other way we can use domains is the following. What I can say is, let's say g of x equals the number of years, or let me say the age of my sister. For whatever reason, we've decided to set up a function that is the age of my sister. So, and I would guess x is probably what year it is. So you plug in the year and you would get out her age. So the domain is the date and the range is her years. So the domain, so let's say that I plug in, let's say x is the date and the age of my sister. The domain on this one would be, well, so I'm going to make up, because I don't think my sisters appreciate, you know, me giving out personal information. So let's say my sister was born in 1980. So the domain would probably make sense that I should start at 1980 and keep going until, I don't know, she's still alive. So I don't have an upper limit on this. We could talk about what we could guess, but I can tell you that x should be at least 1980 for the year, because before that she wasn't around. So how old are you? Like, how old was I before I was born? I mean, that's a philosophical question, but it's not one we can answer with math. So would you know just by looking at the function that you'd need to do this? No. So, and then let's go even further and let's say, well, wait a minute. What ages are reasonable? So I would suggest that an age of 0 is your minimum. And we could argue about whether 0, like 0, when you're a day old, you're not quite a year old, so you're 0 years old. So I think that's a less than or equal to. And then again, we could, if Unfortunately, I picked a really bad example, but I'm just going to soldier through this. I'm going to guess that she probably will not get older than 120 years old. Now, right now, we don't know for sure, but certainly 120 is a good upper bound on the range. It could be that it turns out she only makes it to 119. So at that point, we could change this. But this does not come out of the function itself. It comes out of our understanding of what the function is talking about. So sometimes functions are talking about money, or they're talking about dates, or they're talking about the number of trees, or, you know, the size of your car. And because of that, because of the application of the function, knowing something outside of the function, you get a domain and a range from that. Does that make sense? So these are kind of two different. One type of domain comes because you've got an algebraic instruction that is undefined at certain times. And the other one comes from the fact that our understanding of the meaning of the function has endpoints. So there it goes. And if that didn't make sense, you know, please feel free to ask me more. So let's talk about this last bit. I know this is the world's longest video. And again, my predators of the deep are already asleep. Wake up, wake up. Okay. So if I have f of x equals x over x plus 3, and I've asked you to find the domain. So basically what you need to do is, you know nothing about what the meaning is. So remember, of the two types of the domains, the meaning one with the application, like with my sister's age, that's out the window. We don't know that. All we can focus on is the algebra. So let's look at the algebra here. And the algebra for this is that we've got a fraction. If we have a fraction, we need to make sure the bottom, the bottom, oh my goodness, you can tell. The video's too long. I'm falling asleep. The denominator, there we go, is not equal to 0. And at which point you should say, well, how do I find out when something isn't true? Here's the trick. You find out when it is the truth, and then you skip all those moments. So what does that mean? Take the denominator, set it equal to 0. So this is for fractions. Take the denominator, set it equal to 0, solve for x. When x equals -3, f of -3 equals -3 over 0. Oh no. We got 0 in the denominator. So what do I say for my domain? Here's my fancy domain. Don't let it be -3. That's all. Or, and this horrifies me personally and offends me actually, but I believe that when you turn this in WebAssign, you have to do it like this. So in other words, this is a way to say all the numbers from -infinity up till -3, step over -3, and then keep going. So just skip -3. I personally think this is so beautiful, and I think this is so ugly, but what can you do? Okay, what about square roots? So remember about square roots, which are properly referred to as radicals. I mean, you could talk about square roots, but we're talking about the principal square root. For square roots and radicals, this can be 0 or positive. You cannot, using the real numbers, you cannot put a negative number inside a square root. Now, this is completely a lie, partially a lie. It is true in the real numbers, you can't do this. But in reality, you can do it. You just end up with something called an imaginary number, which we will study later on. So that's kind of cool. But for right now, we're not studying them. We're in the real numbers. Don't let there be a negative number inside. So if we've got radical x, then we need to make sure that x is greater than or equal to 0. That's it. So there's the domain. Domain of G is x stays greater than or equal to 0 or 0 to infinity. Woohoo. Now, I hear you saying, what if I have, I know, what am I doing? It's already a 40-minute video. Oh my goodness, this is the longest video in the history of all. This is like longer than some of the, Avengers movies that probably should have been, trimmed a little bit. What? I didn't say that. Okay. Dun, dun, dun. What if I do something complicated like that? Oh my gosh, how are you going to do this? Well, you just take whatever is inside the radical, which is, fun fact, my least favorite word, the radicand. You take that radicand, there we go, and you set it up to be greater than or equal to 0. And then subtract 1. There's my domain. Domain of H is x is greater than or equal to -1 or from -1 to infinity. From here to eternity. I love you guys for making it through this. You are awesome. You're amazing. You are going to kick butt on this homework. Good luck. Woohoo. Math on. Dance party. See you in the next video.